Start again. All right. So this is it. I'm circulating the test. You can get them back now if you haven't done so. Just pass them on. We're going to start a new chapter. I decided against an extra lecture in collisions. Maybe if this time at the end of the year we'll do that. So collisions, officially this year for the exam anyway, it will be just one-dimensional collisions, which is the easy one. Okay, so the new chapter is on differential equations. We've come across one already, the harmonic equation, x double dot plus omega squared x equals 0. A differential equation is an equation involving a function and its derivatives. The unknown is the function. Unlike an algebraic equation where the unknown is a number, a variable, a scalar, that you have to solve this equation for that value. Here you have to solve an equation for a function. And there are two types of differential equations, ordinary and partial differential equations. So ordinary differential equations, they involve functions of one variable only. And that's all we do this year. So you don't have to worry about PDEs. We'll only be talking about ODEs, ordinary differential equations. And typically, in mechanics, in applied maths in general, you have to solve for a function of time because they mostly arise, those equations, from Newton's second law, for instance, where you have the second derivative of the position, from things like that. Okay? So let's just read this together. Differential equation, equation related function to one or more of its derivatives. The goal is to find all functions that satisfy the equation. And often there are further conditions to be supplied. Typically, initial conditions. You know what's happening at time 0. You want to know what's going to happen at time t later. Primary example is in mechanics, the equation involving the second derivative of the position with respect to time. And in general, f can depend on x. For instance, for simple harmonic motion, f is minus kx, and then you end up with the simple harmonic motion equation. But you can also have f depending on the speed and so on and so forth. So it could be more complicated. Okay? And they also arise in many other applications where mathematical model is being applied. Whether economics, financial maths, biological, population, so on and so forth. So we'll see a few examples of this. Chemistry, radioactivity, a few simple examples, but where it's still possible to make progress, solve the equation, and get a good estimate of what's going to happen. It's all modeling. So modeling, you make an assumption or several assumptions, try to get a nice equation, try to solve it, make predictions, and then you confront them to experiments, and you decide whether the model is accurate or not. Okay? So this is all the blah blah. Here's the number for the attendance today, 6911. Let's get started with our first example. Population models. So that's nice. Very simple example, very powerful though. So Malthus, 19th century, he came up with a model for the growth of populations. Very simple. Let's see what he has. P, capital P for population at time t. Okay, size of some population at time t. Okay, the assumption is that the rate at which it's changed is determined by birth rate and death rate. That's all reasonable. You will expect that. Yeah, that's how populations change. If there's no birth and no death, nothing changes. Okay. So let's see. Let's take a small time interval delta t. is where he said number of births during time delta t. He postulated that it was proportional to the current population. Right? The more people there are, the more children they will have. Makes sense, right? Every couple or every is expected to have, I don't know, 2.1 children. Every cell is expected to divide in 2 or in 3, something like that. So alpha here, that's a constant, a positive constant, and that's called the birth rate. But of course, there's also deaths. And you introduce another constant, but again proportional to the current population. You introduce beta, the death rate. Okay, that's all reasonable. Population proportional, yeah, births proportional to population, deaths proportional to population. What about the change now? Change in population during that small interval of time. So it's going to be population at t plus delta t minus population at p at t. That's the change. And then according to those assumptions, it's going to be plus the number of births and minus the number of deaths. Yeah. And then here I can see I have a common term. So I'm just going to call this gamma, say, where gamma is alpha minus beta. And now I can see something coming along because I have p. Yes, I can link that to the derivative. Yeah, if I was to compute the derivative from first principles, you know that it's the limit pt minus plus delta t minus p of t divided by delta t. That's the definition of the derivative. But that quantity I can compute it from the analysis above. The numerator is just gamma p delta t. The delta t is cancelled out, so the limit is just gamma p. And so I end up with dp dt equals gamma p. That's my differential equation. That wasn't too hard. Yes. That's called Malthus law. The Malthus law. Malthus. And if you look at it closely, you can see it's a differential equation. It's an equation linking a function, p of t, that's what we're looking for, the population type t, to its derivative, its first derivative. So you call that a first order, because the highest order of differentiation in the equation is 1, ODE. First order ODE. You can make a lot of progress for first order ODEs. In fact, that one we know how to solve it. We've seen some techniques earlier. Let's try. Let's try this. So far, so good, yeah? How are we going to do this? How are we going to solve this equation? A function p and a variable t what we're going to do is we're going to use the technique of separation of variables. Yeah, we've done that before. Do you remember? We're going to bring one variable to the left and the other one to the right. We're going to bring all the p's to the left, say, separate variables. So I'm going to bring the p's to the left and the t's to the right. And then I integrate both sides. Then I need to know the integral of 1 over x and the integral of a constant. What is the integral of 1 over p? It's the log, right? That's in the log book. Appropriate name. Makes sense. And don't forget you have to add a constant. Integral of constant is going to be gamma t plus constants, where a and b are constants of integration. Right? That's it. I've solved my differential equation. I could go further. Ultimately, I want to know the population at time t. So can I find p from this equation? Let me see. I can say log of p gamma t plus a minus b. A and b's are constants, so arbitrary constants. So b minus a is also an arbitrary constant. I'm just going to call it c. Now, an equation involving logs, I look in the log book again. I know how to solve it, yeah. It's there on page 21. Log a of y equals x, it means y equals a to the power x. So here, p must be, a is the e number, must be this, yeah? And then I have exponential of a sum. Where is that? Yeah, or it's e, it's the same thing, e to the power a plus b, or a to the power p plus q, right? I can write it as follows. That's the same. Yeah, that's on the top of this page in the logbook. A to the power p times a to the power q is a to the power p plus q. And then e to the power c, exponential c, that's just a constant. So I'm just going to call it d. Okay, and that's it. I've found that p, so p of t equals d exponential gamma t, where d is an arbitrary constant. Often you're linking this to initial conditions at 0. For instance, you know the population at time 0, it's p of 0. That's going to be d to the power 0. E to the power 0 is 1, so that's just d. And so I can write it like this. My solution is equals, yeah, that's it. That wasn't so hard. What do you think? So that's the second differential equation we solved in this course. The first one was the simple harmonic motion. That was second order differential equation. We integrated once to bring it up to first order differential equation, and then we did separation of variables, etc. and found the sign. And two integration constants and so on and so forth. Okay? Sorry? Yeah, let's do it with numbers. That's the general solution. I will work for any scenario, but let's do it for a real life scenario. Well, what's the exponential? You must have seen the exponential function before. You must have seen that it's always a positive constant, a positive function. It can increase or decrease depending on the argument. So t is time, so t increases. So gamma t is going to increase or decrease depending on the size, on the sign of gamma. And gamma, that's the difference between the birth and the death rates. Okay. So if gamma is positive, it's going to be exponential growth. I have this on the right here. And if gamma is negative, you have exponential decay. So exponential growth is the fastest growth you can think of in mathematics. Exponential decay is pretty steep as well, right? After a few units of time, you're down to close to zero. So these are just examples. I took p is 10, gamma is 0.1. Yeah, let's try that. Let's try it, see if it really looks like this. If I go to Wolfram alpha, I can say plot, so what was it, 10 times exponential minus 0.1 times t for t equals 0 to 50. I think that's what I had on the graph. Let's see what it looks like. Yeah, exactly what I have on the lecture notes. And now if I did 2, but with a positive argument, point to t, or until 10 only. If I go to 50, you can see that it just flows up. Very slow at the beginning, and then rapid increase. All right, so that's fair. So it starts at 1, and then increases to infinity very rapidly. No, it starts at 2, sorry. So going back here, in case you didn't know that, it doesn't start at 0, it starts at 2, right? Exponential of 0 is 1, so if p0 is 2, then 1 times 2 is 2. Okay, so far so good. Any questions? Yesterday I got a suggestion for a maths movie quiz. Want to hear it? Yes? From one of you. Something like that. Which movie can that be? So that's from semester 1. Yeah? F to V. What's that? Force times velocity. Yes. What's this? AB. What do you call that object in maths? Power Rangers! Very good. Got it. Okay, let's delete that. But it's recorded now. But is it a movie? Isn't Power Rangers a movie? Yeah? Or is it just a TV show? There is a movie, yeah? Animation? 7 movies, alright. I wasn't sure. Good one. Well done, guys. Okay. So let's do this. This is the numbers that alarmed Malthus in those days. Let's see why he predicted. Let's do this example. US population grew from 3.9 million. Wow, I was a big country then. 3.9 million, that's like less than the population of Ireland now. 1790. To 5.3 million. And still he was worried. He was like, whoa, whoa, whoa. That's not good. Pay attention. Okay, let's do this. Oh, that's good. The results are already given in the text. Yeah, that's why we just saw P0, initial population, exponential gamma t. We know P0 is 3.9. We don't know gamma, but we're given another data. We're told that P of at 10 years later is 5.3. So with these two pieces of information, we should be able to replace in that equation, P0 and gamma. Let's do it. So let's do 10 years by 10 years. That's easier. So if I say T0 in 1790, I know T is 1 in 1800, T is 2 1810, 3 18 to 1820. So I have to add 200 years. So T is 22 2010. So that's the latest date I have a census number. I think that's the latest date. There was a census in the US. But we could go up to 23 and figure out how many people there be in the US in this year, according to that model. So let's go for it. When P is 0, T is 0, P is 3.9. So let's count in millions. And that's going to be P0 exponential gamma 0. That's just P0. Okay, so we found P0. That was easy. To find gamma, we're going to use the other data. We know that P1 is 5.3. And that's going to be P0, which is 3.9, exponential gamma times 1. So now we need an equation for gamma. So I'll let you solve it to find what gamma is. You bring your calculators. Oh, I didn't bring mine, so I'm relying on you. How much do you get? 0.306. 5.3 equals 3.9 times exponential gamma. How am I going to find gamma? Divide across, and then 0.3, 0.30 0.307. Anybody else in that? Yeah? Just to show you the steps, you're going to write that E gamma 5.3 divided by 3.9. So that means, according to page 21, that gamma is the log 0.7 and so on. Okay. So I found Malthus's law as 3.9 times exponential 0.307t, where p is in millions, t is in decades. Okay, so now let's see how good that is. A model, how good a model that is. Yeah. So presumably he wrote that came up with that in 1802, so he was able to predict what would be the population in any time after 1800. Might have been okay. But what about now? What about the later census? Like I say, it's going to be P of 22. In the year 10 years ago, we expect, or we're predicting according to that model, that the population of the US of A should be 3.9 exponential 0 times 22, which is, what you get? Drum rolls. Ta-da. Ta-da. How much do you get? Oh, 23. This year then. But I can't compare it. I don't have census numbers for this year. The census hasn't been conducted yet. 3.3. So here you find 3,344. But that's in million. So that's 3.3 billions. Showing the limits of this model. Clearly, something doesn't add up. Yeah. How much did you get for P of 23 for this year? 4.4 billion. Still be plenty of room for Americans at that number. Yeah. You know that if you use like the density of Manhattan, for instance, you could fill the whole population of the world to something like, I want to say Greece, something like that. Okay, well, in 2010, there was only 310 million people, so it's off by a factor of 1,000, which is pretty bad. Here I plotted, I picked up the census data from Wikipedia. You can find it there, and entered that into a plotting software, and that's the model. So pretty good in the beginning. So you must have been encouraged by a very good match, and then got really scared. But if you remember, exponential just grows. Nothing grows as fast as exponential. And here, look, if I look where we are now, exponential would be 1,000 times, 1,000 units above this. Scary. And so, it's not very good. It's not very good. Only for a little while. And so maybe we could keep elements of this model, but we have to bring in something else. We have to make a more sophisticated model to account for the fact that population growth slows as population increases. Well, it'd be the same if you were to do, I don't know, cell culture in a petri dish. If you were to use just Malthus' law, after so many minutes, you would be predicting that there's more cells than, particles in the universe. So there must be something else at play, right? There's competition, and it's not just death rate that will influence it. There's something else. I'm going to try to do that in the next lecture. What time is it now? Whoa, we have lots of time. Why don't we do past exam papers? What do you say? Did everybody get the test back from last week? Yeah. Everybody got it? Okay. Let's look at past exam papers. What do I have here? Past, there it is. Not private. I cannot, what is going on? I want to. Unbelievable. Let's see with Safari. Yeah. Huh. I understand the risks. Wow. This is serious. Okay. Let's look 2017-18. That was me. So, let's go through the past exam. Oh no, I should have done it here. Yeah, it won't be recorded. How about this one? Short question 8. Monetary investment grows so that if P of t is the balance of an account at time t, then dp dt, how do I add a page? No. What am I doing? Annotate, insert a page, yes. Let's try to do this. So you told that dp dt is 0.1 times p. That's the balance in the account at time t, measured in years. You start with an investment of 100 euros. How long does it take to reach 200 euros? That's the question, right? So, just go back here. Okay, I'll let you try that then. So you might, on the day of the exam, you might remember the formula. P of t equals P0 exponential gamma t, where gamma is now 0.1. Or if you don't, you could do a quick resolution by separating the variables, integrating, and so on and so forth. Whichever way. It'll only take a minute to do that. Then you have gamma, you have P of 0. So you have to find T such that P of T equals 200. That's it. It's a short question. Anybody? Just by substituting. Now it needs to be the same, but how much did you get? Almost 7. Oh, yeah. 69. So why do you have to do 69? So I like that. So it's just one. Wow, it's done. The urine. Yeah, it's on now. I should do it. Why genius? Mathematician wrote the most words. So, some of you got through. Yeah, so either you don't remember the formula and you do the integration by parts. That's how it goes. Integrate both sides. Just like we did earlier. P of 0 is 100. So P of t, or you remember the formula and you write directly, is 100 times 0.1 t. And then you want to find P of t1, say, when the investment has reached 200. So exponential 0.1 t1, 200 divided by 100, that's 2. I take the log on both sides, and then t1 you should find 6.93 and so on years, almost 7 years. So yeah, that's a 10% return rate. That's pretty large. Still takes 7 years. After that, it's going to go much faster. So when you invest, slow at the beginning and then exponential growth. Okay, I'll do another movie quiz. Who votes for another maths movie quiz? Okay, majority. Sorry to the others. Okay, maybe I stop the recording now.